Hey everybody. So we're going to talk now about the law of sines, and this is a useful tool when we're dealing with triangles that are not right triangles. So remember, we've related our trig functions, right? We've related them to right triangles, triangles that have right angles in them, and then the trig functions can be defined as certain ratios of the sides. But not every triangle is a right triangle. And so this is a tool that we'll have to help us when we have one of those triangles. So I've drawn an arbitrary triangle here that might be it's a non-right triangle. There's lots of different ways they can look. I've just picked one, so don't think of this as representing all of the possibilities. Now, when the way we'll use this law in the beginning, and we'll see some applications later, but right now we just want to get used to it. We're going to do what we call solving a triangle. So I want to say what that is before we get to the law, so we see what the goal is. So what we're thinking about doing is solving a triangle. And what we'll mean by this is determine all angles and all side lengths. Okay, so for any triangle, there'll be 6 of these, right? We'll have, and the typical way to talk about them, at least what we'll use is Greek letters for the angles. So we have angles alpha, beta, and gamma. Excuse me. And then across from each of these, we'll use corresponding letters from our alphabet. So the side across from alpha we'll call A, the side across from beta we'll call B, and the side across from gamma we'll call C. So this isn't universal, but something like this is often used. It just makes it easy to talk about. I don't always have to sketch a picture, and we know that when I say angle alpha and side A, you know that I'm talking about the side across from it, right? So this is a nice little correspondence we have just to make things easier. So when we solve a triangle, we will be given some subset of the angles and sides, and we need to find the rest. Right, so there's 6 of them. There's 6 pieces of information we want. We'll be given some of them, a subset. So we'll be given some of those, and then we'll want to find the rest. So there are only a few situations where we can actually make this happen, right? So there's a little bit of intuition behind this, right? If I tell you, for instance, that I have a triangle with an angle of, let's do an angle of, that looks like about 45 degrees. If I tell you there's an angle of 45 degrees, there's no way to tell me the rest of the information about this triangle, right? I can draw a triangle with an angle of 45 degrees. That might be a right triangle. I could also draw one, whoops, that goes something like this. I could draw one that might look something like this, right? I can just keep doing this. All it has to have is that little corner the same, right? So clearly knowing one angle isn't enough to then determine the rest of the triangle, right? What about if we had an angle and a side, right? So I often think about this, imagine something like this, okay? Like a piece of metal bent with an angle. And we want to put some, add some metal to this. How many different triangles could we make out of this? Well, again, it turns out there's an infinite number, because if all I know is this side length is given, this is some length L, and I have some angle theta in here, well, I can extend this side as long as I want, and then there would be a triangle that could work. There would be a triangle that could work. There would be a triangle. There would be a triangle, right? I can keep doing this forever, and all of those triangles would have this angle and this length in them. And so again, it's not determined, right? There's not a single triangle determined by these. So it turns out there are a few situations we'll find ourselves in where it will be determined. Almost. There's one that does have a small amount of ambiguity, but we'll talk about that in a second. So let's go through these three situations. Then we'll build the law of sines and we'll do an example. So the first situation, the first type is called, let's do it here, angle, side, angle, ASA. Angle, side, angle, right? And what this means is we have an angle, a side, and another angle, right? So the side is between those two angles. It's very clear if I give you this information, there's only one triangle that could possibly exist, because I know this side has to continue, pretend my drawing's straight, in this direction. This side has to continue in this direction, and there's only one place they're going to meet, right? There's no other triangle, right? We could turn it around or flip it over, but it's still going to have the same side lengths, the same angle here. So once we know this angle here, and the side between them, there's only one triangle in existence that has that configuration. And so when that's the case, generally speaking, when you have some information that means there's only one possibility, we can usually figure out what that is. And that's the case here. We'll be able to determine when we have this situation. And we'll do I think that's the example we're going to do in just a little bit. There's another situation. Let's do angle, angle, side. Angle, angle, side. So the way I think about this, we've got, let's do it a little out here. We've got an angle and a side that's attached to it. And then there's some other angle. Oops, let me do that again. So should be continuing in the same direction. Okay, so pretend that's about the same. The thing is, we don't know the length of either of the two sides, so this angle can be put anywhere. Well, let's add to this drawing a little bit. So we don't know how long the other two sides are going to be yet, but I know what direction they have to go in, right? So given this third angle, I get like a limit on a constraint on how the other two sides can be arranged. And with that information, right, so I move this around and I see, oh, that's the only place it can be, right? If I move it any closer this way, if I move it any this way, now it's not intersecting at the end of that side. If I move it up there, it's not hitting that angle. So there's really only one place to put this in. And then of course that would tell us how long these other sides have to be, and we would get our triangle again, right? So that was given, let's write this one this way. We were given an angle, and the side between. Here we were given an angle on this side. It turns out we'll have to be able to determine the last two sides in the other angle. And then finally, here's the one with a little bit of ambiguity to it, okay? So side, side, angle. Side, side, angle. So here's how I think about this one. So first, let's draw one of the sides. So when we put two things together, right, just like up here, the angle and the side, there's an angle and a side together, and then another angle that's not attached either. Here we have the side between these two. Here, there's a side and an angle that are together. Let me draw them again as I did. Let's do it this way. There's a side, whoops. There's a side and some known angle. So there's part of our triangle. And then there's going to be another side. I'll draw that in a second, right? So what that means is we know the length here can't change, and we know this angle can't change. So this side that's going to exist over here can be any length. And then we're going to have a side of a certain length coming off of this point at any angle. And here's where the ambiguity comes in. I'll know the length of this side, right? So there's the side, for instance. at some length. Well, somewhere over here, the same length also makes a triangle, right? So it's hard for me to keep this exact. Here, let's do it this way. If I copy and paste, all right, now let's, oh, I thought I could. It doesn't do a good job of letting me just rotate it without changing the side. So I think it's clear. And I made a second video on this, but you can imagine a second side of the same length, right? You can imagine if there's a hinge here, rotating this thing around, right? It would draw a circle, or at least part of one, and intersect somewhere else. And so that's why you sometimes get two possibilities, okay? We call this the ambiguous case. There's a whole separate video on this one. That'll be there, or it is there actually. So I'm not gonna go into any more detail right now. Okay, so all we've said so far is we're looking at non-right triangles, and we're going to try to solve them, meaning we will be given some information about them, and we want to figure out the other information, right? The information here is the measures of the angles or the lengths of the sides, okay? And we've got three situations where this law of sines will come in handy. So let's develop the law of sines. Let's see how we can figure this out. So let's start with, let's draw some triangle. Okay, there's our triangle. I'll label it as I did before. So this will be alpha, beta, gamma. Gammas are a little sloppy, but I'm going to leave it. And then across we have side A, side B, and side C. Okay, so the trick we're going to use is what you can always use if you're in a situation where you don't have, not always, but often use where you're in a situation where you don't have right triangles, but you want some, or but you know that you have trig that uses them, you can create right triangles. So the thing I'm going to do is I'm going to take a line and drop it down from gamma to side C and create a right triangle, right? We call this an altitude. Right, if we're figuring out the area of this triangle, this would be the height. So I'll call it H. Now, there's this triangle we've now created. I'll highlight it in blue here. So we've got this now, we've got a right triangle. This triangle, so let's be a little careful. Side C is this full length, right? We don't know the base of this right triangle. But B is the hypotenuse. We do know that, right? Similarly, gamma, remember, is not the angle for this triangle. It's this full angle up here, and we're missing a little piece of it. But alpha is part of this triangle, okay? This blue triangle. I'll draw that in blue. This side works for the red. Blue. Okay, so now let's use our trig functions. We know that the sine of alpha is the opposite over the hypotenuse. In this case, that's H over B. Okay. And looking at this other triangle, so now we have the same thing happening over here. I can think of, there's a green triangle happening. Right, and this has beta as one of its angles, and it has length A as its hypotenuse, and that's also a right triangle. So in a similar way, I can say that sine of beta equals H over A, opposite over the hypotenuse. Right, so that H, that height, is the opposite on both of these. Well, with a little bit of rearranging, we see that B sine alpha equals H, and A sine beta equals h, which means these two things, b sine alpha and a sine beta, must be equal to each other, right? So b sine alpha is equal to a sine beta. Well, let's divide both sides by AB, right? These are non-zero numbers because of the lengths. We notice the B cancels on this side, the A cancels on this side, and we get sine of alpha over A is equal to the sine of beta over B, right? So the sine of an angle, the ratios of a sine of an angle and the side opposite that angle in these two cases are the same. I'll leave it as an exercise for you, but you can do a very similar thing to find out that we can also add sine of angle gamma over C. Okay, this is our law of sines. Oh, not quite. All right, I guess I'll just do it by hand. This is our law of sines. And again, let's think about what it means. This is telling us that if you take the ratio, in case it's not clear, that arrow tells us where it is. If you take the ratio of an angle, so given any triangle, if you take the ratio of an angle and the side opposite of it, that ratio is constant for all the angles. So maybe a better way to say it, for any given triangle, the ratio of each angle and the side opposite it is a constant, okay? This is always the case. It even works for right triangles, but when it's the case of right triangles, we can just use the regular trig functions. They're designed to work really well with those. But when they're not a right triangle, this relationship works very well for helping us solve the triangles, right? And when there's applications, solving it might mean something important. Okay, let's do an example of this type of problem we might see. So let's suppose we have a triangle. Let me try to draw approximately angle 10. Sorry, this is going to be a side length 10. We're going to have an angle 30 and an angle of 43. So it should look something like this. It's probably not going to be perfectly, that's 30 degrees, that's 43 degrees, okay? So here we have the situation, angle, side, angle, right? So we're given, let's label some things. As usual, we'll call this alpha, beta, gamma. So this length 10 is our side C. We don't know side B. We don't know side A. And we don't know gamma. But I'm going to not write a question mark in there. Well, I can write one in here. This is easy enough. Okay, so how do we solve this triangle, right? We have, let's just make it really clear. We have alpha equals 30 degrees, beta equals 43 degrees, C equals 10. Let's call it inches, feet. So what we're looking for is, we want to know what gamma is. We want to know what B is, and we want to know what A is. Okay, let's start with the easy one. The easiest part about this, right, and this is the case for both these first two situations, they both have two angles in them. So we basically know the third angle, right? This is a very simple computation. We know that the three angles, alpha plus beta plus gamma, are equal to pi, or since this problem is given in degrees, let's say 180 degrees. So gamma is equal to 180 degrees minus alpha plus beta. So in this case, alpha plus beta is going to be 73 degrees. So gamma is equal to 107 degrees. So just like that, we've got gamma. Let's put that in here. Okay. And now we can start using the law of sines. Actually, let's write it here too. We've got 107 degrees. So now let's go after, let's see if we can find side A. Oh, I mislabeled this, sorry. I switched my A and my B. Doesn't change anything about what we need to know. I just wrote too quickly. So what I know is that sine of alpha over A is equal to sine of gamma over C, right? It's also equal to sine of beta over B, but notice I don't know what B is. I'm looking for A. I chose using angle gamma because I know the angle and the side across from it. So this tells me that sine of 30 degrees over A is equal to sine of 107 degrees over 10. We do a little bit of algebra, and we can multiply A to the other side, multiply 10, and divide by sine of 107. We'll get A is going to be equal to 10 sine of 30 degrees over sine of 107 degrees. And this is a calculator problem. 30's on our unit circle, but we don't have any clever way to get the sine of 107 degrees. And so if you punch this into a calculator, the decimal approximation to this is A is equal to, let's go to 2 decimal places. I get 5.23. Okay, so there is A. And this is going to be in feet. And now we can solve for side B in the same way. Just put this in here. Okay, so B will do exactly the same setup. We'll have sine of beta over B is equal to sine of gamma over C. So that looks like sine of 43 degrees over B is equal to sine of 107 degrees over 10, which means B is equal to 10 sine of 43 degrees over sine of 107 degrees, which again, in a calculator gives us approximately 7.13. And there is our B value. All right, so let's just notice a couple of things. A good check is always to have something in our head to see if we've made any silly mistakes, right? So if you picture this triangle, right, 30 and 43 degrees, they're both kind of, they're not that different from each other. And we can kind of imagine how they would point together to make this triangle, right? We don't have something like a 30-degree angle and 100 and something where we're going to get this triangle that goes way, 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 way out before they run into each other, right? So it's kind of nice to just sort of in your head do a little bit of approximating based on what you know. And so this feels like it fits. Also notice that across from the longest side is, or across from the largest angle is the longest side, and across from the smallest angle is the shortest side, right? That's how those ratios have to work. And so if you punch something in wrong and we got this to be, 71 because we missed a decimal point or accidentally hit an extra 0 when we typed that 10 or something like that, that should jump out at us as too big, right? It's bigger than the side across from the biggest angle, and it also just doesn't seem reasonable to think that this side would be 7 times longer than the other one. So when I'm setting these problems up, I try to do a reasonable job of approximating the information I have, right? So if one side is twice as long as the other, I try to draw it approximately twice as big, just so that I get a little bit of insight into what range to expect my answers in. Okay, I think that's it for this video. I have several examples over several videos, and one of them goes into details about that ambiguous case we talked about in the beginning, when we have side-side angle, and the possibility that there might be two triangles that could have the same two sides and an angle, depending on how you arrange that third side. But more on that later. That will be it for this one. Thanks, everybody. I will see you next time.